1 in 4 adults suffers from musculoskeletal conditions, including damage to soft tissues such as ligaments and tendons. Understanding the mechanics of these tissues is essential to the development of effective treatments and injury prevention. Our research group has developed a mathematical model that can accurately predict tendon behaviour. Tendons are made up of fascicles, bundles of collagen fibres called fibrils. Fibrils are up to 60 times thinner than spider silk and crimped. Tendons connect bone to muscle, while ligaments connect bone to bone. Tendons are viscoelastic. Viscoelastic materials combine the mechanical behaviours of viscous fluids and elastic solids. They are described in terms of stress, which is a measure of the force applied to the material, and strain, the degree of deformation in the material. The behaviour of a viscoelastic material is affected by the stresses and strains it has undergone in the past. This memory effect leads to hysteresis, where the graphs of stress versus strain for stretching and releasing the material do not follow the same line but form a loop. Under a constant stress, a viscoelastic material will continue to deform with time. This is called creep. When the stress is removed, the material will slowly recover. Under a constant strain, the force needed to maintain the deformation gradually decreases. This is called relaxation. Our model accounts for viscoelastic creep in tendon fibrils, and by allowing for a distribution of different lengths of fibril within a fascicle, we can predict the complex large-scale tendon behaviour. As a fascicle is stretched, the fibrils inside it straighten. Each fibril has a critical length where it becomes taut and takes up strain. The fascicle gets stiffer as more fibrils reach their critical length. When the force is released, the fibrils slacken. But because of viscoelastic memory, the critical strain at which a fibril straightens will change with each load. We can illustrate the model in 2 tests, a relaxation test and a cycle test. In the relaxation test, the fascicle is rapidly stretched and held for a time, and this is repeated stepwise. Plotting how the stress changes during the test, we can see relaxation occurring each time the stretch is held constant. In the cycle test, the fascicle is gradually stretched and unloaded twice. Fibrils that take up strain in the first stretch have a longer critical length in the repeat. For fibrils that do not straighten fully in the first cycle, the critical length is unchanged. These animations predict how the distribution of fibril lengths in a fascicle changes during the cycle test. We see a marked difference if we do allow for fibril creep on the right compared to if we don't on the left. Taking account of fibril creep allows us to predict how the response of the fascicle to stress and strain will evolve over time. This element of our model fits closely with experimental data and provides a better understanding of tendon behaviour.